I should say that, yes, what I will telling you, it's about polyanalytic function mainly, and an idea to generalize them in hypercomplex analysis, but there are examples which show us that all comes from complex analysis, of course. What is the matter? My first question I will discuss with you is, where come polyanalytic functions from? Maybe you know everything about, but it's interesting that great contributions were given by Musrelishvili, you know very well his name, and we find polyanalytic functions and methods for using polyanalytic function just in plain theory of elasticity. It's not what normally in Clifford analysis or in hypercomplex analysis is discussed, where you have the relation to direct equation, to Maxwell equation, other things, but there are a lot of fields in mathematics where you can useful work with complex analysis. So, yes, here are the basic equations which are described in the chapter of Musrelishvili. Of course, we have here equations of equilibrity, equilibrity with components from extra stresses, with the inner properties of the plate, where we are constructing the Lamé parameters, constants from the materials. And the mathematical theory of elasticity in this way was already developed by Kolosov more than 100 years ago, and his pupil, his student Musrelishvili. I did not know that he was his student. And the beginning of all is the introduction of the Airy stress function. And if you use it for the modeling of these equations, then you have the derivatives, the second derivative related to the stress components. You have the property that the sum should be a harmonic function, and this will allows to come, and this was already noticed by Maxwell, to the biharmonic equation for U, for the area. And this is what explains already in a very famous Gozar's representation theorem of biharmonic functions that this area function can be obtained as a real part of this sum. And here you see phi and psi are holomorphic functions, and z bar is the conjugate complex number. So we have here the structure, which I will show you, which is already considered in quaternionics and three-dimensional elasticity. And this generated the idea, and here we have very important literature about this polyanalytic functions. The definition is therein from Balk. I met him when I was still working in Germany, so I got very early a relationship and to this field. But of course, when you are not working mainly in this field, you forget sometimes. But now, since I saw a lot of articles also in Clifford analysis, where polyanalytic functions are appearing, I was thinking what one can do in a more general setting. So I'm working normally in theoretical parts of Clifford analysis, but I'm looking also where it can be used. And for such a conference, I think it was the idea to show you something what I learned. Here we have, of course, we have the general form mentioned by Balk, that polyanalytic functions are polynomials with respect to the conjugate variable, and the coefficients are holomorphic functions. So that's why if we use the Wirtinger derivatives, the complex partial derivatives with respect to z and z bar, then we can see that a polyanalytic function is the solution of such a differential equation or of the Cauchy-Riemann equation of order n. This is the big difference to the normal treatment. And what happens if we are not looking to the plane, but to the space. Then we have, of course, more stress functions, more dislocation components, and so on, but it's intuitively visible how it works. One has now to find some, let's say, generalization where this stress elements appear. And as I told you, the development in hypercomplex analysis for treating linear elasticity is rather recent, but there were already some ideas. Of course, Kolossow, here's an article in German. I found also an article of Victor Hambatsumyan from 1928 about inverse problems, forgotten also more than 60 years, and then it became one of the basics. So you should not be afraid if somebody after 60 years only comes back and finds what has been done already. So, but you see here is already the expression of the solution by vector and scalar. This smells very much quaternions. Neuber, German, also already early in 1934, tried also to consider solution of spatial problems of elasticity theory, but not in this way. It became possible, and I will show you after, some advances in hypercomplex analysis, because the question of the existence of a hypercomplex derivative was, until the 90s, not clear. I was lucky it was in my PhD thesis that I found some way, and together with my German friend, Görlebeck from Bauhaus Universität in Weimar, we, at the end of the last century, it's so nice to say last century, yeah, we had the idea to interpret, to find the right way to speak about the hypercomplex derivative of monogenic functions. Because
so the second reference, it is Russian, but the title is in French.
Yeah, yeah, they wrote very much in French also. Okay. Yeah, but this, let's say, the citation is in French so that other people could also read it, not knowing directly Russian at the time. So it was interesting. And Hambatsumyan published in German, you see? This was a way to spread.
Also an example of
yeah, exactly, yeah. Yeah, and what I will also mention, these are some special type of polynomials in hypercomplex analysis. After knowing the derivative and remembering that Appel defined some class of polynomials which behave like power-like function, let's say, we worked here with my collaborator in Portugal and used it for generation of monogenic function or generalized holomorphic function, let's say, and a special role had also the generalized exponential, which is using Appel polynomials in the hypercomplex setting and the relationship to Bessel functions. I saw today already several times Bessel, and the exponential function, as we know, as a basic of a lot of mathematics. So, and here are the articles I was referring to. Sebastian Bock was visiting me. He is an engineer. That's why he is dealing with elasticity theory, mechanical engineer. And he came to Portugal and learned with me complex analysis. Görlebeck, as I told you, is my friend of a long time. He was a supervisor, specialized also in numeric analysis. So it was a good collaboration. And nice if you send a student to another place and then brings knowledge to your group. That's very good. Yeah. And here, what are the keywords? First of all, this is really the spatial generalization of this Kolossow-Mussolishvili formula. In elasticity, here is the expression of the displacement and stress formula in terms of two monogenic functions. Again appears this keyword, monogenic function. And then Sebastian used also the ideas of this Appel polynomials to get polynomial basis of solutions for the equation of linear elasticity. And this is a very nice paper, if you read it. Also a nice paper which is completing knowledge and treating this Appel polynomials, and in such a way this article are a good information about elasticity with hypercomplex methods. And what he succeeded, or both, they succeeded to generalize the famous Gaussian representation theory in the algebra, really working with quaternions, not with vector and scalar and so on. And you see here on the left side, this is the area function, the corresponding f, and here you have the scalar part instead of real part of exactly the same expression, but now not with holomorphic functions in C, in the complex plane, but with this generalized holomorphic functions and the conjugated paravector, which is here written. This is a paravector. You can think about A1 and A2 as I and G in quaternionic theory. So, and this allows to modelize the situation in R3. And what is important, this came out in my PhD thesis, to use the Fourier polynomials, the Fourier variables, ZR1 and Z2, already written as two, not at all, I will show you, a little bit different from complex numbers, variables. And then we have here also for the Koolhaas-Moltz-Rishvili formula, I showed you the sum of the stresses here already with 3 components in such a nice presentation. And now I will tell you what are monogenic functions in hypercomplex functions theory. The basics are paravectors. So you have the algebra behind, it's more than quaternions. You have here an orthogonal basis. These are the I, G key in the quaternionic case. Here you have the same properties, non-commutative properties of I, G. And you end up that with this generators, you obtain Clifford algebra, and the degree is growing up to 2 power n. This makes problems to working in R3. You want to stay in the space for modeling relationships in the space in the R3, and you have in the mapping of the original R3, you have in fact a Clifford algebra. And this is technically not difficult, but one has to take care about. So then the general paravector, I showed already the identification of an element in Rn plus 1, and then with this basis here, and then EA, you see, and then we consider this function defined as a function of paravector, and here you have the identification. You have a scalar part and a vector part. It's not possible to avoid to use and to speak about scalar and vector. But what happens here? Of course, how we are looking to these problems is to keep all what you have in complex plane and in the real. So formally similarity to work very easy and in a suggestive way with all what you need. And here we have, of course, a special case for any group 1 gives the complex number. So, but what happens if you now also consider the generalized Cauchy-Riemann operator in Rn plus 1? You have, in fact, the derivative with respect to x0, then to the vector part composed, they give you this generalized Wirtinger derivative or Cauchy-Riemann operator, and all the functions in the kernel of this operator are called monogenic or hyperholomorphic, and so on. And you have to take care that the operator acts from the left or from the right, because you are working in a non-commutative algebra. So, and if you use the concept of Pompeius areolar derivative, then this derivative, which I studied with my colleague, is just from the nature, is a areolar derivative, because you are now in the space. I told last September that one can also to consider this as a function theory in codimension 1. That's what happens here in all these cases. So, and here the areolar derivative is given by the conjugate Cauchy-Riemann operator, and we have the very, very important relationship with the Laplacian, because we have here also a factorization of the Laplacian with the help of these two operators. And so we have immediately also the properties that the real part and imaginary part and all from the relationship between complex analysis and harmonic analysis we have here in our hands. And it happens that now, this was a big problem, that the basic parameter, paravector x, is itself not monogenic with respect to the Cauchy-Riemann operator. So you wanted to look to polynomials with variables which are not monogenic. Normally you have also variables in this field, so, but this is not the case, but one can go around. We see that for x,
So it's not monogenic because you said there's a
here.
commutativity with the d bar.
Yes, this is the reason. But you see, the Cauchy-Riemann operator is not, if you're acting on, here is missing the function, of course, but here it's for x own special. To see that it's not monogenic, you see the result is 1/2 of 1 minus n, and only when n is 1, then we have monogenicity of x, of the paravector. And also the same happens with the derivative given by the conjugate Cauchy-Riemann operator. It gives this value, and if n is 1, we have here, okay, that the complex derivative of the complex variable is 1. So, but here the things are different. And there is, in this sense, essential difference between complex analysis and Clifford analysis if you want directly come to the spatial case or to the general case in Rn+1. So, but it would be nice, you know, all the theory of special functions, a lot of combinatorial problems are depending from the series development. And if you have not these variables, then what to do? So, but here is written what you tell the students already, that just the combination of x and y to the complex variable z and the bar ends up to simplify the differential of a real analytic function. But because this gives 0 for a holomorphic function, and that's very important. This gives a hint how to work in the future. But therefore, you have to consider now in Rn+1 the real differential. And there were in the beginning, and Goldschmidt was my colleague, how many years? 40 years ago. He tried to study the possibility to use other paravectors for a good formulation of linearization problems. Because this would give also this possibility to generalize the complex case easier. Okay, he found that one can introduce this other paravectors with easy using some mapping, ZE, which works, changed to minus AE, and if we have coincidence, it stays as it was. And then you have such a nice matrix. Everything is here presented, all this idea with changing to minus, you see, and it ends up with a conjugate paravector, and it started with a basic one. And what happens? This both, in this construction, this both are commutative. So they are not causing so much trouble. And it's clear that there could exist a special possibility to work with functions only depending from x and x bar. This is a little bit different from the complex case, because the holomorphic function depends only from z, or anti-monogenic, anti-holomorphic only from z bar, only of one of these variables. But as you can see, if we are trying now with the two non-monogenic variables here to consider the same situation, we can determine a gradient to work in these two variables as it would be the two-dimensional case. And the Taylor expansion, because of commutativity, really gives us this presentation, as it would be a series of two variables, real or complex variables. So, and the step now to a generalization is another work of Appel, not about polynomials, but about four types of functions. Hypergeometric special functions. And what is here, what happens? You see, this type of polynomials in x and x bar we found here with, I mentioned already before, we found with this concrete coefficients now. And then if you look now to the Appel's function, okay, Appel polynomial means here only to remember what is an Appel polynomial. It behaves like x power k, the derivative is k times the polynomial 1 degree less, and we have Bernoulli-Hermite polynomials and other polynomials in the set of Appel polynomials in the normal setting. But if you have another derivative, also in the hypercomplex case, then you could use the same property as it was done by Appel. Now, instead of applying the complex derivative, you apply the hypercomplex derivative on paravectors. And what comes out? This Appel 1 function, F1, you find it in the book of Rainville and others, and also on the internet now. If you go to Wolfram, it appears. And they are different because they are convergent in different areas. But F1 is just what we wanted. You see, what is, if this coefficient would be, as we found for the polynomials, here, you see, then we would have this Appel 1 function, a generating function for polynomials, which is also existing. And really, comparing this expression of the coefficients, we only have to see that if you take A as 1, B as n plus 1 half, and B as prime in this form, and now n is because of the factorial, and you use now, instead of U and Y, you use x and x bar. This does not make problems because of commutativity. That's the problem. You can use a generalized, let's say, Appel function working with x and x bar. And so you see we have really a generating function for this Appel polynomials, which, for example, Bock was using in modeling elasticity. So, but there's another problem, and this was also a long-lasting problem, to see what is the right generalization of not the exponential functions, but of the geometric series. These are the both main elementary series in all the analysis. If you go to the book of Rudin, he started the second book, the big one, exactly with a discussion of the exponential function as the most important, but nevertheless, you know, the Cauchy kernel of a holomorphic function in the Cauchy theorem is just the geometric series. So if you want to know what happens with the Cauchy kernel in this easy form, simplified form written, this is a generalized Cauchy kernel for the Rn plus 1. Then you have only to factorize well this expression and to see that here come just this T sk, our coefficients, but also, that's interesting because you have a double sum, this is not directly but with the Pochhammer symbol of k divided by k and then the polynomials. So, and this is of course for a geometric series of order n plus 1. This is the form we would write the geometric series if the variable would be would be real or complex. Yeah. So, and this is not the same, but now we can see that the APL1 function is related to this expression of the fundamental kernel, of the Cauchy kernel. And APL's hypergeometric function mimics only the idea that we know from the geometric series that all is only the sum of all powers of x. And this, the role of x have now in APL1 function, the pk. Our polynomials are polynomials. So, and this is very interesting, and this suggests the following. And here I come just also a very important relationship. If you look to this case of the polynomials, but restricting to x not equal to 0, then you see here appears a polynomial in x vector kappa, and coefficients appear here. And this coefficients we found out also by chance have a very nice relationship to trigonometric sums. Who was speaking? Michael Lacey was speaking today about Vinogradov and the proof of the Goldbach conjecture. It uses trigonometric sums, in fact. And here you see Vietoris, Leopold Willi Torres, an Austrian mathematician. He became 112 years old, very famous, also working in topology. And I have a colleague in Aveiro who is working in category theory with the theorem of Vietoris. So, but we found here that we have in our hand generalized Vietoris numbers, because they are defined with the parameter n, the dimension of the space where we are working. And this caused some results also as a problem of number theory, where we studied with the help of hypercomplex analysis the properties of this sequence of numbers. So, and we introduce the name of generalized Vietoris numbers because he studied this only for the case n equal to 2. Also for the positivity of trigonometric sums in sine and cosine. This is a famous and not known article. It's in the Academy Journal of the Austrian Academy in '58. So also not seen. So, but we have here a generalization. And what is now the end? I showed you how one can work with x and x bar, but then we have restriction. We are not using all the variables or the combinations which are possible. And this is possible if you use the Fourier polynomials, or what Bock was using in his representation. Change, light change, multiplying with a k of the complex number, so changing the real and the imaginary part. Because this is interesting. If you see here, this minus I multiplied by z gives exactly this. And what happens is visible now a duality, because the complex, several complex variable case, where you have two vectors, x and y, multiplied with I to combine to n complex variables. And in our case, we have the real vector and one real variable, and then combining with an imaginary vector of all the generators. So it's so suggestive. And if we were looking now to some results in hypercomplex case, we were also looking to several complex variables because we knew about. And it has to do with a different type of continuation, of course, and it is also the reason why what is one type of Cauchy kernel in representation of functions of several complex variables. This is a multiple geometric series. But I showed you for the hypercomplex case, we need to look to the other type and development of the not multiple geometric series, but this kernel of the Cauchy theorem. And then in matrix form, only to see what happens now with using these variables, there is still one variable, the conjugate is appearing, and the other are all monogenic. You see? And this is very advantageous because if you rebuild now the differential, Then you see if the function is monogenic, then all these coefficients disappear, the dependence from Z bar disappears, and you have only the differential in the monogenic variables. So you can do a monogenic function theory. And of course, the Taylor development we have here with multi-index written, and the product between the variables should be a symmetric product, also some new algebraic ingredients. And what is here important, the variables are looking so when you're working with, but in fact there the x is hidden. X is hidden also with this in this product, in the symmetric product. And what is very nice and should be is that all what you can do with a combination of this product with the variables, also the result of this multiplication is a monogenic function. And then you have everything, you have the Taylor series written with the polynomials, and then I come to the idea. How could we look also to polyanalytic functions? In the same way, but as in the classical case, but now as coefficients of the polynomials in that bar. We know this is the variable which is not monogenic. The other variables are all contained here in the monogenic coefficients. So completely possible from the left and from the right. I remember here by. And now to tell you what I saw, we have a lot of papers from, especially from the group of Daniel Erpay in California, where we have again a consideration of the Fueta variables. We have polyanalytic approach in spaces and Schur analysis. It came also here to say Clifford, and then the last was here about Clifford Appel case, as I told you, but starting from our polynomials, not from the function. And this are other papers. We, for example, use the Appel polynomials to generalize the Laguerre derivative and monogenic Laguerre polynomials. This is the paper where we have this number theoretic aspects of the polynomials. And just some days before I came, I saw that they published also polyanalytic function theory in one complex variables. So this is still alive, polyanalytic. And I thank you for your attention.
Thank you very much.